Tonight, we're going to explore the scariest places in the universe. Not scary in the way a horror movie is scary. Scary in a much deeper way. The way that happens when you understand something at full scale and realize the universe is operating at levels of violence and emptiness and strangeness that dwarf anything the human imagination naturally produces. The kind of scary that makes you feel small, then very quiet, then oddly peaceful. Before we begin, 3 facts. Just 3, then we will spend the rest of tonight explaining them. Fact 1. On December 27, 2004, a dead star, 50,000 light-years away, released more energy in 0.2 seconds than our Sun will release in 250,000 years. The explosion temporarily ionized Earth's upper atmosphere. We felt it, from halfway across the galaxy. Fact 2. Right now, at this exact moment, our entire galaxy, the Milky Way, all 400 billion stars in it, including our Sun, including every planet orbiting every star, including Earth, including you, is being pulled through space at 1.4 million miles per hour towards something massive enough to warp the motion of an entire supercluster. And we cannot see what it is, because our own galaxy is in the way. Fact 3. There is a region of the universe called the Eridanus supervoid. It is 1 billion light-years across. It is essentially empty, not just thin, not just quiet, but emptier than anything our models of how the universe forms could produce. Some cosmologists believe it is the imprint of a collision between our universe and a parallel one pressed into the fabric of space like a bruise. The explanation that doesn't involve another universe is, according to several serious research teams, mathematically insufficient. We are going to start small. We are going to start at the edge of our own solar system, at a boundary you've probably never heard of. And then we are going to build, step by step, outward and upward in scale, through neutron stars and black holes and voids and attractors and the very edge of everything we can see, until we reach the question of what lies beyond the edge. And then we are going to sit with that question for a moment before you sleep. Before we start, if this kind of content, slow, deep, the kind that actually fills your mind with something, instead of just filling it, if that's what you need tonight, please hit like and subscribe to Calm Theory for Sleep. It takes 3 seconds, and it helps this channel reach more people who need exactly this. Now, let's go. The scariest places in the universe don't announce themselves. They don't look frightening from the outside. Most of them look like nothing at all. A dark patch in the sky, an absence, a very faint smear of light that requires a telescope to resolve. The fear comes from the understanding, from knowing what the numbers mean, from doing the conversion and realizing that the scale you're working at has no human equivalent, no frame of reference that makes the quantity feel real. You can say 1 billion light-years, but you cannot feel 1 billion light-years. What you can do after tonight is know it better than you did before. We're going to build this in scale. Each place we visit will be more extreme, more remote, more violent, or more incomprehensibly empty than the last. By the end of the countdown, we will have moved so far beyond the familiar that the opening items, things like Magnetars and black holes, will feel almost cozy by comparison. That's the point. Perspective is everything in cosmology, and tonight we're going to earn some. Let's start at the boundary of our own solar system. Because even here, at the closest possible scale, the universe is already doing something remarkable. The sun doesn't just emit light, it emits matter. Constantly, in all directions, at speeds between 250 and 500 miles per second, a stream of charged particles, protons and electrons, the shredded remains of hydrogen atoms heated to temperatures of millions of degrees in the sun's corona, flows outward into space. This is the solar wind. It is not a metaphor. It is a real flow of real particles, and it extends in a bubble around the entire solar system. That bubble has a boundary. At a distance of roughly 85 to 95 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, about 93 million miles, the solar wind runs into a problem. It has been expanding and decelerating for billions of miles, and at this point, the pressure of the interstellar medium outside pushes back hard enough that the solar wind has to slow down. Not gradually, abruptly. The solar wind is traveling at several times the local speed of sound in the plasma. When it hits the back pressure of interstellar space, it forms a shock wave, a wall of compressed, superheated plasma where the supersonic wind suddenly becomes subsonic. This is the termination shock, and Voyager 1 crossed it on December 16, 2004, at about 94 astronomical units from the Sun. The instruments registered the deceleration in real time. The solar wind slowed from roughly 400 miles per second to about 100 miles per second. The temperature of the plasma jumped by a factor of 20. The density increased. The magnetic field compressed. All exactly as predicted. But the exact distance was wrong. Scientists had predicted 75 to 90 astronomical units. Voyager crossed at 94. The boundary was nearly 1 billion miles further out than the best models suggested. And the shape was not the clean sphere they predicted. Voyager 2, crossing on August 30th, 2007, crossed at 84 astronomical units, 10 AU closer than Voyager 1. The two spacecraft were heading in different directions. The fact that they crossed at different distances proved the heliosphere is not spherical. It is compressed in the direction the Sun is moving through the galaxy and extended in the opposite direction. It breathes. It shifts with solar activity. It is not a fixed wall. It's a dynamic, asymmetric bubble that changes shape depending on what the Sun is doing and what region of interstellar space the solar system is currently moving through. The termination shock matters for us because it's the edge of the environment the Sun creates. Inside the termination shock, the solar wind dominates. Magnetic fields, particle energies, the overall environment, all of it is controlled by the Sun. Outside the termination shock, a transition region called the heliosheath exists before you reach the heliopause, the true boundary where the Sun's influence ends and interstellar space begins. Voyager 1 crossed the heliopause in 2012 at 121 astronomical units. It has been in interstellar space for over a decade. The reason this matters as a starting point for tonight's countdown is what it illustrates about scale. The termination shock is 94 astronomical units from Earth. That's about 8.7 billion miles. Voyager 1, traveling at 38,000 miles per hour since 1977, took 27 years to get there. A beam of light takes about 13 hours to cover that distance. And yet, in the context of everything we're going to discuss tonight, the termination shock is right next door. The nearest star is 270,000 astronomical units away. The center of the galaxy is 1.7 billion astronomical units. What lies beyond the observable universe is by definition unreachable at any speed. We start at the termination shock, not because it's the scariest place. It isn't, not even close, but because it's where the familiar ends. Everything beyond it is, in some meaningful sense, out there. And tonight, we're going out there. Now we step up in violence by several orders of magnitude. Now we talk about Magnetars. A Magnetar is a type of neutron star, and we'll get to what neutron stars are in the next section, but with a magnetic field so extreme that it occupies a category of its own. The strongest magnetic field we can create in a laboratory on Earth is about 45 Tesla. A refrigerator magnet is about 0.001 Tesla. An MRI machine is about 3 Tesla. The magnetic field of a magnetar is approximately 100 billion Tesla. Let that sit for a moment. Not 100 times stronger than an MRI. Not 100,000 times. 100 billion times stronger. At that field strength, something happens that has no equivalent in any environment we can create or study directly. The electromagnetic field becomes so intense that it distorts the shapes of the electron orbitals in atoms. Atoms, the building blocks of all matter, with their electrons in precise quantum shells that determine every chemical property of every substance, become physically deformed by the magnetic field. An atom anywhere within about 1,000 kilometers of a magnetar would have its electron cloud stretched and compressed along the field lines. Its chemistry altered. Its behavior changed in ways that make the chemistry we know on Earth impossible. If you could somehow stand 1,000 kilometers from a magnetar, which is already far inside the region where every other force would have killed you, the magnetic field alone would distort the atoms in your body before any other effect finished the job. This is not radiation damage, not heat, not gravity. This is the fundamental electromagnetic structure of matter being distorted by field strength. The Magnetar, SGR 1806-20 sits about 50,000 light-years from Earth, on the far side of the Milky Way. It was identified in 1979 and has been monitored since. It is roughly 20 kilometers across. It weighs more than 1.4 times the mass of the Sun. A teaspoon of its material would weigh approximately 1 billion tons on Earth. Not because of any exotic chemistry, because of density. The density of matter at the core of a magnetar reaches or exceeds nuclear density, the point where protons and neutrons are packed as close together as they physically can be. There is no such thing as an empty space between atoms. There are barely any atoms. Just neutrons, crammed against each other. Quantum degeneracy pressure, the only force keeping the object from collapsing further into a black hole. The surface of SGR 1806-20 is not a smooth sphere. It has a crust, a solid outer layer made of iron nuclei in a crystalline lattice, threaded with magnetic field lines of incomprehensible strength. Occasionally, the crust cracks, not because of external impact, but because the magnetic field evolves and shifts, and the stresses it puts on the solid crust eventually exceed what the crust can hold. When a section of the crust snaps, what physicists call a starquake, energy stored in the magnetic field is released, and the amounts of energy are staggering. The Magnetar is the most extreme object in the known universe that isn't a black hole. It's the place where matter is at its most compressed, its most magnetized, its most energetic, still recognizable as matter. It occupies the very edge of what matter can be, before the laws of physics require it to become something else entirely. December 27th, 2004. This date is marked in astronomical records in a way that deserves to be more widely known. At 21 hours, 30 minutes and 26 seconds UTC, a burst of gamma rays and X-rays from SGR 180620 reached Earth. What the instruments recorded in the first 0.2 seconds of that event represented more energy than the Sun will emit in 250,000 years. All of it, in 1/5 of a second, from a dead star 50,000 light-years away. The Earth responded. The ionosphere, the layer of Earth's upper atmosphere that is partially ionized by the Sun's ultraviolet radiation, was measurably affected. The gamma rays from SGR 180620, crossing 50,000 light-years, arriving at Earth, were still intense enough to ionize atoms in our atmosphere at an altitude of about 85 kilometers. Ground-based magnetometers, instruments that measure fluctuations in Earth's magnetic field, registered a disturbance. Satellites in low Earth orbit detected the event across multiple wavelength ranges simultaneously. This happened from halfway across the galaxy. Think about what that means in terms of scale. Light takes 8 minutes to travel from the Sun to Earth. It takes 4.2 years to reach the nearest star. The light from SGR 180620 has been traveling for 50,000 years, crossing the full diameter of our galactic disk, passing billions of stars. And after 50,000 years of travel, it was still strong enough to noticeably affect the atmosphere of a planet. Scientists calculated what the same event would look like from closer distances. At 10 light-years, a distance containing about 2 star systems, the gamma-ray flux would have been 200 billion times more intense than what we received. It would have stripped the ozone layer of any Earth-like planet on the near side of the burst. Not damaged it. Stripped it. Completely. Permanently, on the timescale of life's recovery. At 1 light-year, the surface sterilization would be total and nearly instantaneous. The flare lasted about 0.6 seconds in its initial intense phase, followed by a fainter oscillating tail lasting several minutes. In those fractions of a second, SGR 180620 outshone every other source of electromagnetic radiation in the observable universe. Every star in the Milky Way, all 400 billion of them, simultaneously combined. All of that output was less than what this one dead star, 20 kilometers across, put out in 0.2 seconds. That is shocking discovery number 1. The universe is capable of violence at scales that, even at interstellar distances, are capable of affecting our planet. We are not as isolated as the emptiness of space might suggest. We exist within reach, within detectable, measurable, atmosphere ionizing reach of some of the most energetic events in the cosmos. The comfort, such as it is that SGR 180620 is 50,000 light-years away, in the opposite part of the galaxy from us. The nearest known Magnetar to Earth is about 1,000 light-years away. At that distance, a major Magnetar flare would be spectacular, but harmless. The energy flux would be far below what would significantly affect our atmosphere. We are, for now, in a relatively quiet neighborhood. A Magnetar is a neutron star. But before we can understand what makes a Magnetar extreme, we need to understand what a neutron star is. Because a neutron star, without any magnetic superpowers, is already one of the most bizarre objects in the observable universe. When a star between about 8 and 20 times the mass of our Sun reaches the end of its life, it has exhausted its nuclear fuel. For millions of years, the star has been supported against its own gravity by the outward pressure of nuclear fusion reactions at its core. Hydrogen fuses to helium. Helium fuses to carbon. Carbon fuses to neon, then oxygen, then silicon. Silicon fuses to iron, and then it stops. Iron is the end of the line for stellar fusion. Iron has the highest binding energy per nucleon of any element, which means fusing iron into heavier elements requires energy input rather than producing it. A star with an iron core has run out of options. The fusion that was holding it up stops, and the core, now around 1.4 solar masses of iron, collapses. In about a quarter of a second, a volume of gas the size of Earth's orbit collapses to a sphere about 12 kilometers across. The collapse happens at a quarter of the speed of light. The resulting rebound shockwave tears the outer layers of the star apart in a supernova explosion that briefly outshines entire galaxies. What remains at the center is a neutron star. A neutron star typically has a mass of 1.4 times our Sun and a radius of about 10 to 12 kilometers. The density at its core is on the order of 10 circumflex, 17 kilograms per cubic meter. At that density, all the empty space in atoms has been squeezed out. Electrons and protons have been forced together by the immense pressure to form neutrons. The neutrons are packed together at nuclear density, a state of matter that doesn't have a normal name, because it doesn't exist anywhere else in the universe except in these objects, and for fractions of a second in certain particle collider experiments. The surface gravity of a neutron star is about 200 billion times Earth's surface gravity. If you dropped a marshmallow from 1 meter above the surface of a neutron star, it would hit the surface at about 2 million miles per hour and release energy equivalent to a nuclear weapon. The escape velocity from the surface is about 0.4 times the speed of light, 40% of c. To leave the surface of a neutron star, you need to be traveling at 120,000 kilometers per second. Any slower, you come back. The surface temperature of a newly formed neutron star is around 100 billion Kelvin. As it cools, it drops over thousands of years to a mere 1 million Kelvin, still 175 times hotter than the surface of our Sun, but considered cold in the neutron star context. The crust that forms as it cools is stranger than any material we can create. A lattice of iron nuclei, threaded with electrons moving at relativistic speeds, overlying layers of increasingly bizarre nuclear matter. Below the crust, there may be a superfluid of neutrons, a liquid with zero viscosity, flowing without any friction or resistance. Below that, the physics is uncertain. Theorists disagree about what happens at the very center of a neutron star. Some models predict strange quarks. Some predict kaon condensates. Some predict structures that don't have names, because we don't know if they exist. This is what a normal neutron star is. Now imagine one with a magnetic field 1,000 times stronger than average neutron stars. That's a magnetar. There are about 3,000 known pulsars, a type of neutron star we'll discuss shortly, in the Milky Way, and perhaps 30 known magnetars. Given the size of the galaxy and the rate of supernovae, there are probably around 1 billion neutron stars in total, most of them cold, dark, and virtually undetectable, drifting through interstellar space. Some of them are heading our way. None of them are close enough to matter. But they are out there in enormous numbers, the remnants of stars that were once burning for millions of years, now reduced to city-sized spheres of degenerate matter, moving silently through the dark. Neutron stars don't always drift alone. Sometimes they're born in binary systems, two massive stars orbiting each other that both eventually explode and leave behind two neutron stars, now orbiting each other. And neutron stars in binary systems do something remarkable over millions of years. They spiral inward. As two neutron stars orbit each other, they lose energy by emitting gravitational waves. Ripples in the fabric of space-time, predicted by Einstein's general relativity in 1916, and first directly detected only in 2015. The gravitational wave emission is tiny in any individual orbit, but over millions or billions of years, the energy loss adds up, and the orbits decay. The two neutron stars spiral closer and closer and closer, and then, at the end, they merge. The merger of two neutron stars is one of the most violent events in the observable universe. In fractions of a second, two objects, each containing more mass than our Sun, each the size of a city, traveling at a significant fraction of the speed of light, collide. The collision produces a burst of gravitational waves so powerful it can be detected billions of light-years away. It produces a short gamma-ray burst, a burst of gamma radiation of extraordinary intensity lasting from a fraction of a second to a few seconds. And it produces a kilonova. A kilonova is an explosion about 1,000 times brighter than a typical nova, but still thousands of times fainter than a supernova. It occurs when the debris from the neutron star merger, a hot, dense soup of neutrons and heavy nuclei, is ejected into space and undergoes rapid nuclear reactions. And these reactions produce heavy elements, specifically elements heavier than iron, gold, platinum, uranium, iodine, barium, strontium. The full periodic table from roughly iron up through uranium. On August 17, 2017, something happened that changed astronomy forever. At 12:41 UTC, the LIGO and Virgo gravitational wave detectors simultaneously registered a gravitational wave signal. A 100-second chirp, rising in frequency as two neutron stars spiraled toward each other. 1.7 seconds later, the Fermi Gamma-Ray Space Telescope and the Integral satellite detected a short gamma-ray burst from the same location in the sky, a galaxy called NGC 4993, 130 million light-years away. For the next several weeks, every major telescope on Earth and in space turned toward that galaxy. They watched a point of light that hadn't been there before brighten, shift color, and fade. The spectrum of that light, the signature of specific elements absorbing and emitting specific wavelengths, revealed the chemical fingerprint of freshly made heavy elements. Strontium was confirmed. Gold was there. Platinum was there. The merger of two neutron stars, 130 million light-years away, had been directly observed simultaneously in gravitational waves and light for the first time in history. GW17, 0817, the most important astronomical event of the 21st century to that point. The moment we confirmed what had been theorized for decades about where heavy elements come from. This is shocking discovery number 2. And unlike many things in cosmology that require some adjustment of intuition, this one is simply true and requires nothing but the fact itself. Every piece of gold anywhere on Earth, your jewelry, the gold in electronics, gold bars in vaults, the traces of gold in certain foods, the gold used in cancer treatments, The gold in every wedding ring that has ever been placed on a finger. Every gram of that gold was created in a collision between two neutron stars. There is no other known process in the universe that produces gold efficiently enough to account for the amounts we observe in the universe. Gold cannot be made in ordinary stellar fusion. The heaviest elements that stars like our Sun can produce during normal burning are in the range of carbon and oxygen. Massive stars, in the final seconds before a supernova, can fuse up to iron. But iron is element 26. Gold is element 79. The gap between iron and gold requires a process called rapid neutron capture, or R-process nucleosynthesis, in which atomic nuclei capture multiple neutrons in extremely rapid succession, faster than the resulting unstable nuclei can decay. This requires a neutron flux of extraordinary density, far more intense than a typical stellar interior or a standard supernova. The two confirmed environments where this can occur are Magnetar-enhanced supernova explosions and neutron star mergers. Current evidence suggests neutron star mergers are the dominant source. When Earth formed 4.5 billion years ago, it formed from a cloud of gas and dust that had already been enriched by previous generations of stellar explosions. The heavy elements in that cloud, including all the gold, were there because, billions of years before the Sun existed, somewhere in our galactic neighborhood, neutron stars were merging. The gold incorporated into the early Earth mostly sank to the core during the period of differentiation, when the planet was molten and heavier elements migrated toward the center. The gold we find accessible at and near the surface was delivered later, by asteroid impacts, during the late heavy bombardment period, around 4.1 to 3.8 billion years ago. Those asteroids also got their gold from neutron star mergers. So, two neutron stars orbit each other for perhaps 1 billion years. They spiral together, losing energy to gravitational waves. They merge in a fraction of a second. The kilonova explosion scatters gold and platinum and uranium across the surrounding space. Over millions of years, this material becomes part of molecular clouds. The clouds collapse. New stars form. Planets form around those stars. The gold is incorporated into planetary bodies. Asteroids carry it. An asteroid impacts a young planet. The gold reaches the surface. 4.5 billion years later, a being on that planet shapes the gold into a ring and places it on another being's finger and calls it a symbol of permanence. The gold in that ring has traveled from a neutron star collision to a molecular cloud, to a protostellar disk, to an asteroid, to a planet, to a mine, to a jeweler, to a ceremony. It is older than Earth. It is older than the solar system. It was made in violence so extreme that it briefly outshone the galaxy, and it arrived here by a chain of catastrophes so improbable that the ring exists only because every link in that chain held. That is what gold is. That is what valuable means in a cosmological context. When a neutron star forms from a stellar collapse, it almost always inherits angular momentum from the star it came from. And because it has collapsed to a tiny fraction of the star's original size, conservation of momentum causes it to spin up dramatically. A star that rotates once a month becomes a neutron star that rotates many times per second. The fastest known pulsars rotate over 700 times per second. 700 rotations per second. A pulsar is a neutron star with a misaligned magnetic field. The magnetic poles don't line up with the rotation axis. So as the star spins, the beams of electromagnetic radiation it emits sweep through space like lighthouse beams. If one of those beams sweeps past Earth, we detect a repeating pulse of radio waves. The timing of those pulses is extraordinarily regular, in many cases more accurate than atomic clocks. Jocelyn Bell Burnell was a 24-year-old graduate student at Cambridge University when she discovered the first pulsar in 1967. She had spent months building a radio telescope covering 4.5 acres and hand-analyzing the paper printout of data, literally miles of paper, scrolling through the data looking for patterns. In August 1967, she noticed a repeating signal with a period of 1.3373.0119 seconds. Precise, Machin-like, utterly unlike anything natural was expected to produce. The signal was so regular that for a brief period, her research group seriously entertained the possibility that it was artificial. They nicknamed the source LGM-1, Little Green Men 1. Not because they believed it, they didn't, but because they had to consider the hypothesis before ruling it out. The signal was too regular to be a natural oscillation of a gas cloud or a star. It was eventually identified as a rotating neutron star after more such signals were found in other directions, and the astrophysics was worked out. The 1974 Nobel Prize in Physics was awarded for the discovery of pulsars. It was awarded to Jocelyn Bell Burnell's supervisor, Anthony Hewish, and to radio astronomer Martin Ryle, not to Bell Burnell herself. This remains one of the most discussed controversies in the history of Nobel Prizes in physics. Millisecond pulsars, the fastest spinning ones, can achieve timing precision that rivals or exceeds the best atomic clocks on Earth. The pulsar PSR J0437-4715, about 510 light-years away, rotates 174 times per second, and has been timed with a precision of about 100 nanoseconds. You can use it as a clock. Cosmologists do. Arrays of pulsars, distributed across the sky, form what's called a pulsar timing array, essentially a galaxy-scale detector for gravitational waves at very low frequencies corresponding to the orbital periods of pairs of supermassive black holes merging over millions of years. In 2023, several pulsar timing array collaborations around the world simultaneously announced strong evidence for a gravitational wave background. A hum of gravitational waves permeating the universe, produced by the population of merging supermassive black holes throughout cosmic history. The universe has a gravitational wave heartbeat, and pulsars are the instruments with which we hear it. A pulsar, in the end, is both the most exotic clock imaginable and one of the universe's most useful scientific instruments. It is the dead heart of a former star, spinning hundreds of times per second, beaming radiation across light years, with a precision that allows astronomers to test general relativity, detect gravitational waves, measure interstellar plasma, and probe the properties of matter at nuclear density. It is one of the universe's stranger jokes that something so violent in its creation, the collapse of a massive star in a supernova explosion, ends up being one of the most precisely regular, most scientifically useful objects in the cosmos. When a star is massive enough, above roughly 20 solar masses, the collapse at the end of its life cannot be stopped, even at nuclear density. The neutron degeneracy pressure that holds up neutron stars is insufficient for a core that massive. The collapse continues past neutron star density until it reaches a singularity, a point of infinite density where the known laws of physics break down. The region around the singularity from which light itself cannot escape is a black hole. The event horizon is the defining feature, of a black hole. It's not a physical surface. There's no wall, no membrane, nothing you could touch if you were falling toward it. The event horizon is a mathematical surface, the boundary in space-time beyond which the escape velocity exceeds the speed of light. Cross the event horizon, and no matter how fast you move in any direction, you cannot move fast enough to return. The geometry of space-time inside the event horizon is fundamentally different from the geometry outside. The future is toward the singularity. You can no more avoid reaching the singularity than you can avoid tomorrow. The nearest known stellar mass black hole to Earth is Gaia BH1, discovered in 2022 using the Gaia astrometric satellite. It is approximately 1,560 light-years away. There are estimated to be somewhere around 10 million to 1 billion stellar mass black holes in the Milky Way. The uncertainty is enormous, because we can only detect them when they're interacting with nearby matter. The ones drifting alone in interstellar space are, for all practical purposes, invisible. Cygnus X1, discovered in 1964, was the first black hole candidate to be identified. It's a stellar mass black hole in a binary system, orbiting a companion star and pulling gas off of it. The gas forms an accretion disk, a swirling disk of superheated materials spiraling inward, that emits X-rays so intense that Cygnus X1 is one of the brightest X-ray sources in the sky. The Cygnus X1 black hole has a mass of about 21 solar masses. Its Schwarzschild radius, the radius of its event horizon, is about 62 kilometers. A sphere 62 kilometers across, inside which sits 21 times the mass of the Sun, and from which nothing can escape. The process called spaghettification would kill you long before you reached the event horizon of a small black hole. As you approach, the gravitational force on your feet is stronger than the force on your head, because your feet are closer to the center of mass. This tidal force stretches you along the radial direction and compresses you sideways. For a stellar mass black hole, these tidal forces become lethally large well outside the event horizon. You would be stretched into a long, thin stream of matter, spaghettified, before reaching the boundary. For a supermassive black hole, the event horizon is so large that tidal forces at the event horizon are relatively gentle. You'd cross the event horizon without feeling anything unusual. The tidal destruction would come later, closer to the singularity. Just outside the event horizon, at 1.5 times the Schwarzschild radius, is the photon sphere. This is where gravity is strong enough to trap light in circular orbits. A photon moving tangentially at exactly the right distance will orbit the black hole indefinitely, bending in a perfect circle. If you were at the photon sphere, you could, in principle, see the back of your own head. Light that left your head traveled around the black hole and arrived back at your eyes. Black holes evaporate. Stephen Hawking showed in 1974 that quantum mechanical effects near the event horizon cause black holes to slowly radiate energy, what's now called Hawking radiation. The rate of evaporation depends on the mass. Smaller black holes evaporate faster. A stellar mass black hole would take approximately 10 circumflex, 67 years to evaporate, far longer than the current age of the universe. But given enough time, the most extreme object in the universe fades away, leaving nothing, not even the singularity. At the center of the Milky Way, 26,000 light-years from Earth, something sits in the dark. We cannot see it directly with optical telescopes. The galactic center is obscured by dense clouds of gas and dust that absorb visible light completely. But radio waves, infrared light, and X-rays pass through those clouds. And with those wavelengths, astronomers have been mapping the galactic center for decades. What they found at the very center is a compact radio source, a point-like emitter of radio waves far brighter than anything around it. It was named Sagittarius A, pronounced A-star, in 1974. For decades, the nature of this object was debated. Then, astronomers began tracking the motion of individual stars near the galactic center, using infrared observations from large telescopes equipped with adaptive optics systems that corrected for atmospheric distortion. The stars near Sagittarius A are moving in elliptical orbits, and the orbits are fast. The star designated S2 has an orbital period of about 16 years, meaning it completes a full orbit around the galactic center in 16 years. For reference, Earth completes an orbit in 1 year at a distance of 1 AU from a star of 1 solar mass. S2's orbit allowed astronomers to directly calculate the mass of the object at the center, approximately 4.15 million solar masses, confined to a region smaller than our solar system. The only object consistent with those properties is a supermassive black hole. Sagittarius A is a supermassive black hole with a mass of 4.15 million suns. Its Schwarzschild radius, the radius of its event horizon, is about 12.4 million kilometers. For comparison, the Sun is about 1.4 million kilometers in diameter. The event horizon of Sagittarius A is about 8.5 times the diameter of the Sun. You could fit the Sun inside the event horizon of our galaxy's central black hole and have room to spare. On April 10, 2019, the Event Horizon Telescope collaboration published the first direct image of a black hole, M87. The supermassive black hole at the center of the galaxy, Messier 87, 53 million light-years away. On May 12, 2022, they published the second, Sagittarius A, itself. The image shows the ring of glowing gas around the shadow of the event horizon, a bright ring of light bent by the extreme gravity around a central dark region. Our galaxy's central black hole, imaged directly for the first time. The image was constructed by combining data from 8 radio telescopes distributed across Earth, effectively creating a telescope the size of our planet. Sagittarius A is currently relatively quiet. It has occasional flares, bursts of X-rays and radio emission lasting hours, but is not actively consuming large amounts of matter the way quasars do. Astronomers believe this is partly because its environment is currently somewhat gas-poor compared to what it was in the distant past, when it was likely much more active. In a few 100 million years, the Milky Way will merge with the Andromeda Galaxy, and the collision will send enormous quantities of gas raining down toward both galactic centers. Sagittarius A will wake up, and for a period of tens or hundreds of millions of years, the center of our galaxy will blaze with the energy of an active galactic nucleus, possibly bright enough to affect the entire Milky Way disk. Shocking discovery number 3 comes from the orbit of S2, the star that has been most precisely tracked around Sagittarius A. At its closest approach to the black hole, called periapsis, S2 comes within about 120 astronomical units of Sagittarius A. For reference, that's roughly the distance from the Sun to the inner edge of the Oort cloud. It sounds far, but around a 4 million solar mass black hole, 128 U is extremely close. At that point, S2 is traveling at about 7,650 kilometers per second, approximately 2.7% of the speed of light. To put that in context, the fastest spacecraft humans have ever launched, Helios 2, reached about 70 kilometers per second. The proton beams in the Large Hadron Collider are accelerated to 99.999999% of the speed of light. The speed of light itself is about 300,000 kilometers per second. S2, a normal star about 15 times the mass of our Sun, is moving at nearly 8,000 kilometers per second. Not because it's been accelerated artificially, not because of any exotic process, just because it's orbiting something 4 million times the mass of the Sun at close range. Gravity did this. At 2.7% of the speed of light, relativistic effects become measurable. Time passes slightly slower for S2 at periapsis than for the instruments watching it from Earth. Its light is slightly gravitationally redshifted. The orientation of its orbit precesses, drifts forward, in a way that only general relativity can explain. Exactly as Mercury's orbit precesses around our own Sun, but vastly more dramatically. These effects have been measured directly. In 2018, the Gravity Collaboration detected the gravitational redshift of S2's light as it passed through periapsis. The direct observation of Einstein's prediction that light climbing out of a gravitational well loses energy and shifts to longer wavelengths. They were measuring the prediction of general relativity in real time, watching a star fall toward a 4 million solar mass black hole, and observing that the light leaving that star had been stretched by gravity before it reached our telescopes. There are around 100 known stars in the inner parsec of the galactic center, within about 3.26 light-years of Sagittarius A. Many of them are young, massive, blue stars. This presents a mystery. Stars this young and this massive should not be able to form so close to a supermassive black hole, because the tidal forces would tear apart any gas cloud before it could collapse to form a star. They must have formed farther out and migrated inward, or they were formed in some process we don't yet understand. The galactic center is one of the most scientifically active areas of current astronomy research, because it is simultaneously the nearest supermassive black hole, an extreme environment, and a puzzle we haven't solved. Sagittarius A is a quiet giant, but in the early universe, supermassive black holes weren't quiet. They were the most luminous objects the universe has ever produced. A quasar, short for quasi-stellar radio source, a name that reflects the confusion of early observers who couldn't figure out what these point-like objects were, is what you get when a supermassive black hole is actively consuming enormous amounts of material. As gas and dust and stars fall toward the black hole, they form an accretion disk, a flattened structure of intensely heated material spiraling inward at relativistic speeds. The temperature in the inner accretion disk reaches tens of millions of Kelvin. The material glows with extraordinary luminosity across the entire electromagnetic spectrum. Some of the infalling material is redirected into jets, narrow beams of plasma launched perpendicular to the accretion disk and traveling at close to the speed of light, extending for millions of light years. The quasar 3C273, the first quasar identified and still one of the nearest, is about 2.4 billion light-years away. Its luminosity is about 4 trillion times the luminosity of our Sun. It is visible with a small amateur telescope from Earth, and it is 2.4 billion light-years away. To put that in perspective, the Andromeda Galaxy, the nearest large galaxy to the Milky Way at 2.5 million light-years, requires a dark sky and careful observation to see with the naked eye. 3C273, nearly 1,000 times farther away, is bright enough to detect with a modest telescope. The quasar era peaked around 10 billion years ago, when the universe was about 3 billion years old. In that era, galaxies were richer in gas, mergers were more frequent, and supermassive black holes were more actively fed. The early universe was ablaze with quasars. Looking at very distant galaxies with powerful telescopes, we see quasars at enormous distances. And because light from those distances has been traveling for billions of years, we're seeing the early universe. The most distant known quasar is at a redshift of about 7.5, meaning we see it as it was when the universe was only about 700 million years old. Its black hole already had a mass of about 800 million solar masses. Explaining how a black hole that massive formed so early in the universe's history is one of the central unsolved problems in cosmology. As galaxies age, their gas supply decreases. The supermassive black holes at their centers consume the available material, then run out. The quasar switches off. The Milky Way's central black hole went through active phases in the past. There is evidence of a major burst of activity about 3.5 million years ago that produced what's called the Fermi bubbles, two enormous lobes of high-energy gas extending about 25,000 light-years above and below the galactic plane. A sleeping dragon with evidence of past fire still written across the sky. Sagittarius A has 4.15 million solar masses. It's the center of our galaxy. It's the largest black hole in our immediate neighborhood. It seems unimaginably large. TOM 618 has 66 billion solar masses. 66 billion. That number, 66 billion times the mass of the Sun, puts TOM 618 in a class that challenges not just intuition, but models. The theoretical mechanisms that allow supermassive black holes to grow are, at this mass, strained. A black hole can only grow so fast, limited by what's called the Eddington luminosity, the point where the radiation pressure from the infalling material becomes strong enough to blow away the gas that's feeding the black hole. The most massive black holes we know of appear to require either longer time periods than the universe has provided, or super Eddington accretion rates that the standard physics of accretion disks struggles to produce. TOM 618 is one of several ultramassive black holes that sit at the extreme end of this problem. TOM 618 was discovered in 1957 and initially catalogued as a blue stellar object. Its true nature as a quasar wasn't established until 1970. It lies about 10.4 billion light-years from Earth, which means we're seeing it as it was when the universe was only about 3.3 billion years old. At that time, it was already one of the most luminous objects in the universe. Its luminosity is estimated at about 140 trillion times the luminosity of our Sun. 140 trillion suns worth of light, pouring out of a region barely larger than our solar system. The Schwarzschild radius of TOM 618, the radius of its event horizon, is approximately 1,300 astronomical units. Our solar system, measured to the orbit of Neptune, extends to about 30 ATU. The inner Oort cloud, the distant sphere of comets surrounding the Sun, begins at around 2,000 to 5,000 AU. TOM 618's event horizon is 1,300 ATU in radius, meaning the event horizon of this single black hole is comparable to the scale of our entire solar system, out to the cometary reservoir. The Sun, all 8 planets, all their moons, the asteroid belt, the Kuiper belt, and the inner Oort cloud. All of it would fit inside the event horizon of TON 618 with room to spare. What does it mean to say something fits inside an event horizon? It means that if you were at a distance of 1,380 U from TON 618, you would be inside the point of no return. The Sun and all its planets could be relocated to that position, orbiting TON 618 at 1,380 U. And every single one of them, every atom on every world, would be inside the event horizon. All of it would be falling toward the singularity. None of it could escape. A beam of light crossing the full diameter of TON 618's event horizon, 2,600 astronomical, would take about 7.5 days to make the journey. And the light would be doing this inside an event horizon. It would never get out. This is shocking discovery number 4, and it requires a moment to absorb properly. The event horizon of TON 618 is 1,300 astronomical units in radius. That is 1,300 times the distance from Earth to the Sun. The orbit of Neptune is 38 U. The orbit of Pluto at its farthest point is about 49 ATU. The termination shock, where Voyager 1 crossed in 2004, is around 94 AU. The heliopause, the boundary of the solar system, is around 120 AU. All of those features of our solar system, from the innermost planet to the outermost reach of the Sun's influence, fit within a radius of 120 ATU. The event horizon of TON 618 has a radius of 1,300 ATU. You could take our entire solar system, Sun, planets, Voyager 1 and Voyager 2, the heliopause and all, and drop it inside the event horizon of TON 618 with 1,188 U of room to spare in every direction. What would it look like from the inside? Nothing dramatic. Immediately. If you were somehow instantaneously placed at the event horizon of TON 618 with no velocity relative to the black hole, the tidal forces at that location would be extremely mild, a consequence of the event horizon being so large that the gradient in gravitational force across the size of a human body is negligible. You wouldn't feel yourself being stretched. You wouldn't feel the heat of an accretion disk. You'd be at the event horizon, not in it. The geometry of space-time around you would be unusual, but physically you'd feel normal in the immediate moment. And then, as your future inexorably led toward the singularity, as you fell inward and time passed and tidal forces grew, you would eventually, on a timescale of hours perhaps, reach regions where the forces became lethal. But the crossing of the event horizon would be, experientially, undetectable. This is perhaps the most unsettling thing about large black holes. The event horizon is not a physical object. It is a region of space-time defined by what is possible, not by anything you could see or feel. You could cross the event horizon of TON 618 without knowing it, without any instrument detecting the transition. And once you had, nothing, no engine, no signal, no escape attempt, could undo it. There are known black holes even larger than TON 618. Home 15A, in the Abell 85 cluster, has an estimated mass of 40 billion solar masses by some measurements, possibly as high as 66 billion. The black hole in the galaxy cluster, Abell 1201, has been estimated at 32 billion solar masses. ultramassive black holes, defined as those above 10 billion solar masses, appear to inhabit the centers of the largest, oldest elliptical galaxies, the products of billions of years of galactic mergers and feeding. They are the largest single objects in the universe. Nothing else comes close to their mass, their gravitational influence, or the sheer scale of their event horizons. If the black holes we've discussed so far are alarming because of their size, rogue black holes are alarming for a different reason. They're everywhere. They're invisible. And you'll never see one coming. When two galaxies merge, a process that takes hundreds of millions of years and is one of the primary mechanisms by which galaxies grow, the supermassive black holes at their centers eventually find each other, spiral together, and merge. But in the chaotic gravitational dynamics of a galaxy merger, not all the black holes in the system end up at the center. Stellar mass black holes, the remnants of dead massive stars, can be ejected from star clusters and galaxies by gravitational slingshot interactions. Multiple black hole systems are inherently chaotic. Three black holes interacting gravitationally will more often than not eject one of them at high velocity. The Milky Way is estimated to contain between 10 million and 1 billion stellar mass black holes. Most of them have never been detected. They produce no light. They don't emit radio waves. They don't shine in any wavelength. They are black in the most absolute sense. Objects that emit no radiation except the extraordinary faint trickle of Hawking radiation. Far too weak to detect from any distance. We detect black holes when they do one of two things: consume nearby matter, producing X-rays and jets, or pass in front of a background star, producing a gravitational lensing event, where the background star temporarily brightens and distorts. In 2022, a team analyzing 6 years of Hubble Space Telescope observations of a gravitational microlensing event confirmed the detection of a rogue stellar mass black hole drifting through the Milky Way. The object, designated MOA 2011, BLG 191, OGLE 2011, BLG 0462, is estimated to have a mass of about 7.1 solar masses. It is located approximately 5,000 light-years away. It is drifting through the galaxy with no star to orbit, no accretion disk, nothing to make it visible. Only the gravitational distortion of background starlight revealed its presence. This is the first isolated stellar mass black hole, confirmed by direct observation. There are estimated to be tens of millions more in our galaxy alone. They are distributed throughout the galactic disk and halo, moving with the velocity dispersion of old stars, following trajectories determined by a billion years of gravitational interactions. Some of them, on the longest timescales, will eventually pass through star-forming regions or dense interstellar clouds and begin accreting material, briefly lighting up as X-ray sources before moving on. But most will drift forever in silence, invisible, passing through the spaces between stars without ever coming close enough to any star system to make their presence known. They do not pose a practical threat to Earth or the solar system. The nearest known black hole, at 1,560 light-years, is not approaching on any collision course. The probability of a rogue black hole coming close enough to the solar system to cause any gravitational disruption in the next billion years is essentially zero. Space is simply too vast. But they are there, in very large numbers, invisible, moving. We have established that a Magnetar flare is more energetic than the Sun will produce in 250,000 years. Now we need to go higher. Gamma-ray bursts are the most energetic individual events in the observable universe. A long gamma-ray burst, lasting from a few seconds to several minutes, releases more energy in those seconds or minutes than the Sun will release over its entire 10 billion-year lifetime. The total energy output, primarily in gamma rays, can be as high as 10 circumflex 47 joules. For comparison, the energy of a supernova explosion, already an event that outshines an entire galaxy for weeks, is about 10 circumflex 44 joules. A gamma-ray burst is 1,000 times more energetic than a supernova. Long gamma-ray bursts are produced by collapsar events, the collapse of a massive, rapidly rotating star, leading to the formation of a black hole surrounded by an accretion disk that drives relativistic jets of material along the rotation axis. These jets, launched at close to the speed of light, bore through the collapsing star and emerge, driving a shockwave into the surrounding medium that produces the gamma-ray emission. The jets can extend for millions of light years. Short gamma-ray bursts, lasting less than 2 seconds, are produced by the neutron star mergers we discussed earlier. Confirmed when GW17-0817 produced a short gamma-ray burst detected 1.7 seconds after the gravitational wave signal. GRB2, detected on October 9, 2022, was immediately recognized as something extraordinary. Nicknamed BOAT, the brightest of all time, it was the most energetic gamma-ray burst ever detected, and possibly the most energetic single event observed by humanity in the history of astronomy. It was so bright that it saturated most of the gamma-ray detectors pointed at it, requiring reconstruction of the event from the few instruments that weren't overwhelmed. Its afterglow, the longer wavelength emission that follows the initial burst as the jet slams into surrounding material, was visible for months, and the highest energy photons detected from it exceeded a tera-electron volt, more energetic than anything the Large Hadron Collider produces. It was 2.4 billion light-years away. Scientists are still analyzing its data, and preliminary results suggest it challenges current models of how gamma-ray bursts produce such high energy emission. The afterglow of a gamma-ray burst is visible for weeks or months after the initial burst, in X-ray, optical, and radio wavelengths, as the jet continues to interact with the surrounding medium. These afterglows can be detected from the other side of the observable universe. The most distant gamma-ray burst detected, GRB 090. 423, occurred at a redshift of about 8.2, meaning its light has been traveling for about 13.1 billion years. We see it as it was when the universe was only about 630 million years old. Now we change the character of the scary. Everything so far has been violent, energetic, things happening on scales that make human experience feel microscopic. But from here, the fear shifts. From here, it's about absence, about the particular horror of the universe's emptiness. In 1981, astronomer Robert Kirshner and his colleagues were conducting a survey of galaxies in a region of sky toward the constellation Boötes. They were mapping the three-dimensional distribution of galaxies by measuring their distances using the Doppler shift of their light. And they found something that shouldn't be there. A hole. Not a metaphorical hole. A region of space approximately 330 million light-years across that was nearly empty of galaxies, where thousands of galaxies should have been, based on the average distribution in the surrounding universe. there were only about 60. The Boötis void is not a region of low density. It's a region of almost no density. The galaxies that do exist within it are concentrated near the edges, as if pressed there by the same dynamics that shaped the void in the first place. 330 million light-years. Let's put that in perspective. The Milky Way is about 100,000 light-years across. The distance to the Andromeda Galaxy is about 2.5 million light-years. The Boötis void is 330 million light-years across. You could fit 3,300 Andromeda Galaxy separations end-to-end inside the Boötis void. You could line up over 3,000 Milky Ways across its width. If the Milky Way were at the center of the Boötis void, we would not have discovered any other galaxy until the 1980s. The nearest galaxies would have been at the edge of the void, 165 million light-years away, barely detectable with the telescopes that existed before about 1990. The universe forms structure through gravity. Dark matter clumps first, and ordinary matter follows, forming filaments and sheets and nodes. The cosmic web, where galaxy clusters and superclusters form at the intersections of filaments. Between the filaments are voids, regions relatively poor in matter that was drained toward the denser filaments over billions of years. Voids are a normal feature of the cosmic web, but they should not be 330 million light-years across. The largest voids predicted by standard cosmological models are about 150 to 200 million light-years. The Boötis void is larger than those predictions. Not dramatically larger, but enough to be a statistical oddity, something that appears to occur rarely, if at all, in large computational simulations of structure formation. The void might be a chance superposition of several smaller voids that appear connected from our viewing angle. It might be a genuine large void formed by some combination of initial density fluctuations and subsequent dynamics that our models underpredict. Or it might be pointing towards something that standard models don't capture. When Gregory Tucker, one of the team members who studied the Boötis void, described it, he reportedly said, "If the Milky Way had been in the center of the Boötis void, we wouldn't have known there were other galaxies until the 1980s. A civilization that evolved in the center of the Boötis void would have looked out at their night sky and seen, instead of our rich field of nearby galaxies and star clusters, an almost perfect darkness. The same physics, the same stars, the same civilization, and an almost completely different view of the cosmos around them. The Boötis void is 330 million light-years across. Now we look at something nearly 3 times larger. The Eridanus supervoid was identified through an anomaly in the cosmic microwave background radiation, the afterglow of the Big Bang, a faint glow of microwave radiation that fills all of space and represents the universe, when it was only about 380,000 years old. This background radiation is extraordinarily uniform. It is the same temperature in every direction to about 1 part in 100,000. The tiny fluctuations that do exist encode the seeds of all structure, the slightly denser regions that would eventually collapse to form the cosmic web we see today. But the WMAP satellite, mapping the CMB with unprecedented precision in the early 2000s, detected something that immediately attracted attention. In the direction of the constellation Eridanus, a large region of the CMB was measurably colder than the surrounding area, about 70 microkelvin below the average. This might sound tiny, 0.00007 degrees, but in a CMB that varies by only about 0.0003 degrees across the entire sky, a cold spot this large and this consistently cold stands out statistically. When astronomers mapped the distribution of galaxies in the direction of the Eridanus cold spot, they found what you'd expect, relatively speaking, if a supervoid existed there. A region significantly underdense in galaxies, extending from about 600 million to 3 billion light-years from Earth, centered in the direction of the CMB cold spot. The void is estimated to be about 1 billion light-years across. 1 billion light-years. The Boötes void, 330 million light-years across, could fit inside the Eridanus supervoid 3 times over, with room to spare. Why does a void produce a cold spot in the CMB? Through what's called the integrated Sachs-Wolf effect. When a photon, a particle of light, travels through a void, it climbs out of the relatively shallow gravitational well of the underdense region. In an expanding universe, the void's gravitational potential changes as the photon is traversing it. The potential becomes shallower during the crossing, and the photon emerges with slightly less energy than it should have. Slightly cooler. This effect is small for individual voids, but a very large, very deep void can produce a measurable temperature decrement in the CMB. The problem is that the integrated Sachs-Wolf effect from a void the size of the Eridanus supervoid, with the density contrast we observe, cannot fully account for the temperature deficit of the cold spot. The cold spot is colder than the Eridanus supervoid alone can explain. Something else is needed. Shocking discovery number 6 is the most speculative item in tonight's countdown. And I want to be honest about that. But I also want to be honest about what speculative means here. It means a hypothesis proposed by serious scientists in peer-reviewed literature, motivated by a real mathematical problem, for which the standard explanation is insufficient. In 2006, cosmologist Laura Mersini-Houghton and colleagues proposed that the CMB cold spot in Eridanus could be explained by a quantum entanglement effect between our universe and a neighboring universe, in the multiverse landscape of eternal inflation. The idea, in simplified form, is this. During the inflationary period immediately after the Big Bang, different regions of our universe might have been in quantum contact with the space of the larger multiverse. If our universe's inflationary patch was adjacent to another bubble universe, another region of space-time that also underwent inflation and became a separate universe, the interaction between them could have left an imprint. The gravitational interaction between 2 neighboring bubble universes would create a region in our universe where matter was slightly depleted, a void, and where the CMB would appear slightly colder. In other words, the Eridanus supervoid might be a bruise, the place where our universe collided with, or was pressed by, or was gravitationally influenced by, another universe. During the first fraction of a second of existence, when what became our universe was smaller than a proton. The prediction of the theory was specific. If the cold spot is a bubble universe collision imprint, it should be associated with a supervoid. The supervoid should have specific properties, and the overall statistical anomaly of the cold spot should exceed what standard cosmological models can explain. The Eridanus supervoid has been confirmed. Its properties are broadly consistent with what collision models predict, and the cold spot does remain statistically anomalous, even after the void is accounted for by standard ISW effects. This does not prove the multiverse. It doesn't prove bubble universe collisions. The Eridanus cold spot has mundane potential explanations that cannot be ruled out. A statistical fluctuation, an underestimated systematic in the CMB maps, a void that is somewhat denser at its edges than models allow. The universe doesn't require us to invoke another universe for any observation we have currently made. But the possibility, the genuine scientific possibility, taken seriously by people who work on cosmology professionally, that we might be looking at the imprint of contact between our universe and another, is one of the most profound ideas in contemporary physics. And the data is there. The cold spot is real. The void is real. The standard explanation is insufficient. Those are three facts. The multiverse explanation is one hypothesis for reconciling them. 1 billion light-years of emptiness, possibly created by contact with something we cannot observe, will never visit, and cannot reach. A scar on the universe's oldest light, marking where something larger than our universe touched it. We've talked about places that emit things: radiation, gamma-ray bursts, gravitational waves. Now we talk about something that does nothing but pull. Something that pulls everything in a 150 million light-year region toward it, including us. In 1986, a team of astronomers studying the motions of galaxies in the local universe noticed something strange. The Milky Way and all the galaxies around it, the local group, the Virgo cluster, galaxy clusters throughout the local supercluster, were all moving in the same direction. Not just in the direction of the expansion of the universe, which carries all galaxies apart from each other. A peculiar velocity on top of the expansion, directed toward a specific point in the sky. The point was in the direction of the constellation Centaurus, in the southern sky. And the team, trying to characterize what could produce the gravitational pull necessary to move our galaxy at hundreds of kilometers per second, estimated the mass of the attractor at roughly 10 circumflex, 16 solar masses, roughly 10,000 times the mass of the Milky Way, contained in a region a few 100 million light-years across. They called it the Great Attractor. Our galaxy is moving toward the Great Attractor at approximately 600 kilometers per second. The Milky Way, 400 billion stars, all of its mass, you, this moment, this planet, all of it is currently moving at 600 kilometers per s in the direction of the Great Attractor. This motion is in addition to the overall expansion of the universe and the Milky Way's orbit within the local group. There's a problem with observing the Great Attractor. It's in the zone of avoidance. The galactic plane, the band of the Milky Way running across the sky, is thick with gas and dust that blocks visible light. The Great Attractor lies almost directly behind the galactic plane from our perspective. Optical telescopes cannot see through the galactic disk. This is why it took until the 1980s to characterize the Great Attractor at all. With X-ray telescopes and radio telescopes that penetrate the galactic disk, astronomers have been mapping the region behind the zone of avoidance for decades. What they've found at the heart of the Great Attractor is the Norma cluster, a rich cluster of galaxies at the center of the Norma supercluster. The Norma cluster alone contains hundreds of galaxies. But the Norma cluster itself is just the densest node in a larger structure, the Hydra Centaurus supercluster, a collection of galaxy clusters and filaments that represents the actual source of most of the gravitational pull. The Milky Way will never fall into the Great Attractor. The expansion of the universe, dark energy pushing space apart, will eventually dominate over the Great Attractor's gravitational pull. In a few tens of billions of years, the universe's accelerating expansion will carry our galaxy away from the Great Attractor region faster than gravity can pull us toward it. We are, right now, in the window of time when the Great Attractor's gravity is significant enough to generate our peculiar velocity. but not significant enough to overcome cosmic expansion on long timescales. The Great Attractor pulls our entire supercluster toward it, but the Great Attractor itself is moving. In 2000, detailed analyses of galaxy peculiar velocities in the broader region revealed that the Great Attractor wasn't the terminal destination of the gravitational flow. The Hydra Centaurus supercluster, the structure at the core of the Great Attractor, is itself moving. And it's moving towards something even larger, farther away, the Shapley supercluster. The Shapley supercluster, named for the American astronomer Harlow Shapley, who first noted the region's unusual density of galaxies in 1930, is the most massive known concentration of matter in the observable universe, within a few hundred million light-years. It is located about 650 million light-years from Earth. It contains approximately 10,000 galaxies in dozens of galaxy clusters, with a total mass estimated at around 10 circumflex, 17 solar masses, roughly 100 quadrillion times the mass of the Sun, and about 100 times the mass of the Great Attractor region. The influence of the Shapley supercluster on the motion of our galaxy has been estimated to be comparable to, or slightly less than the influence of the Great Attractor. Some analyses suggest the Shapley supercluster accounts for about 40% of our peculiar velocity. Others suggest more. The relative contributions of the Great Attractor and Shapley to our galaxy's peculiar velocity are still being actively studied, as new galaxy surveys progressively map the full three-dimensional structure of the local universe. What pulls the Shapley supercluster? Is Shapley itself in motion? The answer is almost certainly yes. There are no objects in the universe that are truly stationary. Every galaxy, every cluster, every supercluster is moving with a peculiar velocity determined by the gravitational influence of everything else in the observable universe. The Shapley supercluster is itself moving in a direction determined by the integrated pull of every mass concentration it has ever interacted with. Mapping these flows, the peculiar velocity field of the local universe is an active area of cosmological research. The flows extend to the limits of what we can measure, which brings us to something that doesn't have a name yet. Or rather, something that has a name but isn't yet fully understood: dark flow. In 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper with a startling claim. Using the kinematic Sunyaev-Zeldovich effect, the subtle distortion that galaxy clusters imprint on the cosmic microwave background as their hot electrons scatter CMB photons. They detected a coherent bulk motion in a sample of about 800 galaxy clusters. The clusters were moving, not in random directions, as expected from gravitational interactions within the observable universe. Not in directions that matched what the Shapley supercluster or any other known mass concentration could explain. They were all moving in approximately the same direction, toward a specific point in the sky, with a velocity of around 600 to 1,000 kilometers per second. And the remarkable part, this coherent motion extended out to 2.5 billion light-years from Earth, not 150 million light-years like the Great Attractor's influence zone. Not 650 million light-years like the Shapley supercluster. 2.5 billion light-years, 1/4 of the way to the edge of the observable universe. Kashlinsky named this phenomenon dark flow, by analogy with dark matter and dark energy, something real and measurable that we don't have a good explanation for within standard cosmology. The standard model of cosmology, Lambda CDM, the Lambda cold dark matter model, is extraordinarily successful at explaining the large-scale structure of the universe. Galaxy distributions, the CMB power spectrum, the age of the universe, the expansion history. All of it fits. And within lambda CDM, coherent bulk flows on the scale of 2.5 billion light-years should not exist. The gravitational influence of structures within the observable universe is not sufficient to produce a coherent flow over that distance and at that velocity. All known mass concentrations, including Shapley, should account for the flows we observe on scales up to a few 100 million light-years. Beyond that, the flows should be random. If dark flow is real, there is a mass concentration outside the observable universe, beyond the cosmic horizon. That is generating a gravitational pull large enough to produce a coherent bulk motion in galaxy clusters across 2.5 billion light-years. A structure we cannot see, cannot detect directly, and cannot reach, but whose gravitational influence is detectable in the motion of everything we can observe. The Planck satellite, with its more precise CMB maps, did not confirm dark flow in its 2013 and 2015 analyses. The statistical significance of the Kashlinsky result has been debated. Some analyses find it consistent with zero. No dark flow, the original detection was a statistical artifact. Others find marginal consistency with a real signal. The question is genuinely unresolved. But if dark flow is real, if the signal Kashlinsky detected is genuine, then the universe beyond the cosmic horizon is not simply more of the same. It contains something massive enough to deflect the motion of matter across billions of light-years of the observable universe. Shocking discovery number 7 is not about violence or mass. It's about the structure of knowledge itself. About what it means to live in a universe where some questions have answers that are permanently inaccessible. If dark flow is caused by a massive structure outside the observable universe, then that structure exists in a region from which no light has ever reached us, and never will. The observable universe is defined by the cosmic horizon. The distance light can have traveled since the Big Bang, adjusted for the expansion of the universe. This horizon is at about 46.5 billion light-years from Earth. Beyond it is space that is real, that exists, that contains matter. But the light from that space has not had time to reach us. And because the universe is expanding, because space itself is growing, the most distant regions are receding from us faster than light can travel. They are moving away from us at superluminal speeds. Not violating relativity, it's space itself expanding, not anything moving through space. But the effect is the same. The light from those regions will never reach us. The horizon is a permanent, fundamental limit on what we can ever observe. If dark flow points to a structure beyond the horizon, then that structure is beyond the causal horizon of our universe. It will never be in causal contact with us. No signal from it will ever reach us. No photon from any star or galaxy in that region will ever enter our observable universe. We cannot, even in principle, with any conceivable technology, send a probe there or receive a signal from it. It is real, it is massive, and it is permanently, irrevocably beyond our reach. This is the most fundamental kind of scary in tonight's countdown. Not violent, not energetic, not directly threatening. Just a clean, absolute physical limit. A wall in the structure of the universe itself. Not a wall made of matter, but a wall made of the finite speed of light and the infinite expansion of space. That separates us permanently from things that are real and may be vast. We do not know what is beyond the cosmic horizon. We know it exists. We know from our best models of cosmic inflation that the universe extends far beyond the observable portion, possibly infinitely far, possibly for distances that make the observable universe's 93 billion light-year diameter look like a proton compared to the Earth. We know it contains matter, probably organized in a cosmic web similar to the one we observe locally. We know it has regions of high density and low density, voids and superclusters and galaxy clusters, structured by the same physics that structured everything we can see. But the specific structures are unknown. The specific contents of that beyond are unknown. And if dark flow is real, something specific over there, something with a specific location, a specific mass, a specific history, is pulling on everything we can see, and we will never know what it is. Let's stand at the edge for a moment. The observable universe has a radius of approximately 46.5 billion light-years. It is a sphere centered on Earth, not because Earth is special, but because the observable universe is defined by what we can see, and we can only see from where we are. Any observer anywhere in the universe has an observable universe centered on themselves, with the same 46.5 billion light-year radius. The number 46.5 billion might surprise you if you know the universe is 13.8 billion years old, and light travels at a fixed speed. If the universe is 13.8 billion years old, shouldn't the most distant thing we can see be 13.8 billion light-years away? The answer is no, because the universe is expanding. When the light from a distant galaxy began its journey, the galaxy was much closer. As the light traveled, the universe expanded, carrying the source galaxy farther away. By the time the light arrives at Earth, the galaxy that emitted it is now 46.5 billion light-years away, even though it was only 42 million light-years away when the light left. At the very edge of the observable universe, the cosmological horizon, we're not seeing the edge of the universe. We're seeing the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang, emitted 380,000 years after the Big Bang, when the universe first became transparent. The surface of the CMB is not a physical surface. It's a surface in time, the moment when light could first travel freely. Everything we see beyond the CMB, beyond the surface of last scattering, is inferred from the physics of the early universe, not directly observed. At the cosmic horizon, space is receding from us at the speed of light, due to the expansion of the universe. Beyond the horizon, space is receding faster than light. This doesn't violate relativity. Nothing is moving through space faster than light. It's space itself that's expanding. But the consequence is the same. Photons emitted by objects beyond the horizon are moving away from us, in terms of the light's progress through the expanding space, even as the light itself moves toward us at sea. They will never arrive. The light is fighting a battle against the expansion of space it cannot win. The observable universe contains approximately 2 trillion galaxies. Earlier estimates suggested about 200 billion, but a 2016 analysis accounting for galaxies too small and too faint to detect directly raised the number to about 2 trillion. These 2 trillion galaxies contain a total of roughly 10 circumflex 24 stars, 10 septillion stars. And this is only the observable portion, the fraction of the universe from which light has had time to reach us. Beyond the observable portion, the universe continues. The question is, how far? The universe beyond the observable horizon is not empty. It's not a wall. It's not a special region. It's by every indication more universe. More galaxies, more stars, more planets, more cosmic web, extending in every direction beyond what we can see. How far does it extend? The answer depends on physics we don't fully understand yet. If the universe is spatially flat, as observations of the CMB strongly suggest, then there are no preferred directions, no overall curvature, and the geometry allows the universe to be spatially infinite. An infinite universe would contain infinite galaxies, infinite stars, infinite planets, and, by extension, if you accept that physical conditions and initial conditions vary randomly, an infinite number of places where conditions like Earth's arise, and an infinite number of beings like us. This is the implication of straightforward cosmology if the universe is infinite, and the laws of physics are the same everywhere. This doesn't mean everything exists. It doesn't mean the laws of physics vary. It means that, in an infinite universe with random initial conditions, every configuration that is physically possible will appear somewhere. And, in an infinite space, not just once, but infinitely many times. The theory of cosmic inflation, the exponential expansion that occurred in the first 10 circumflex 32 seconds after the Big Bang, suggests the universe is far, far larger than the observable portion. Different inflation models give different estimates, but many suggest the total universe extends at least 10 circumflex, 23 times farther than the observable universe, in every direction. That number, 10 circumflex 23, is approximately the number of atoms in 100 grams of matter. The observable universe, which already contains 2 trillion galaxies, would be a single atom in a structure the size of a human body. Some inflationary models predict eternal inflation. The inflation never stops globally, but locally regions stop inflating and become observable universes. Bubble universes, each with their own physical constants and properties. In eternal inflation, our observable universe is one bubble in a vast, possibly infinite collection of bubbles, each of which contains its own 2 trillion galaxy observable region. The bubbles are causally disconnected. They can never interact. They are, in a physical sense, separate universes. This is the multiverse. Not one universe, but a structure containing an effectively infinite number of universes, each with their own physical laws, constants, initial conditions. In most of them, the laws are wrong for complexity. Particles that won't bind into atoms, forces that won't allow stars, constants that produce universes that collapse in a fraction of a second or expand so fast that no structure ever forms. But in some of them, possibly many of them, conditions allow galaxies, stars, planets, chemistry, life. We cannot test this directly. The other bubble universes are beyond our horizon, receding faster than light. No probe can reach them. No signal from them can arrive here. The multiverse is a consequence of mathematical models that successfully predict things we can observe, extrapolated to regions we cannot. Whether this extrapolation is justified, whether the multiverse is a prediction or a metaphysical framework, is one of the central debates in contemporary theoretical physics. But this is where tonight's countdown ends. At the edge of the observable universe, looking out at the darkness of the beyond, knowing that out there, in some region we will never see, never reach, never directly know anything about, are things that may include other universes, other versions of physics, and by every probabilistic argument, structures so vast they make everything we've discussed tonight seem like a local detail. There is one final place on tonight's countdown. It's not a location in space, it's a location in time. the farthest future we can trace using physics. The heat death of the universe is the state toward which everything in the cosmos is moving. It is the endpoint of the second law of thermodynamics, applied at the largest possible scale. The second law says entropy, the measure of disorder, of unavailable energy, always increases in a closed system. The universe is a closed system. Its entropy is always increasing, and the end point of maximum entropy is a state in which no further increase is possible, a state of perfect thermodynamic equilibrium. In that state, there are no temperature gradients, no concentration of energy, no free energy available to do work. Nothing can happen, because happening requires a temperature difference, an energy gradient, a region of order that can become disorder. When everything is at the same temperature, when all gradients have been erased, nothing more can occur. This is the heat death, and the timeline to get there is staggering. In 10 circumflex 14 years, 100 trillion years, roughly 7,000 times the current age of the universe, the last star will exhaust its fuel and fade. The era of stars will end. The universe will be populated by black holes and the cold remnants of stars, white dwarfs, neutron stars, brown dwarfs, objects radiating away the last of their heat into the darkness. In 10 circumflex, 40 years, if proton decay occurs at the rate predicted by some grand unified theories, all ordinary matter will have decayed. Protons and neutrons will have dissolved into lighter particles, primarily positrons and neutrinos. White dwarfs and neutron stars will evaporate, not through any violent process, but through the gradual statistical decay of their component protons. The universe will be populated by black holes, electrons, positrons, photons, and neutrinos. From 10 circumflex 67 to 10 circumflex 100 years, a range so large that our number system barely has adequate language, the black holes will evaporate through Hawking radiation. The smallest, lightest black holes will go first, evaporating in bursts as they reach their final moments. The supermassive black holes, the giants like Tom 618, with masses of 66 billion solar masses, will be the last. The most massive black hole takes an estimated 10 circumflex 100 years to evaporate completely. This is called a googol year. One googol is 10 circumflex 100. The universe will be older than a googol years when the last black hole goes. After all the black holes are gone, the universe contains only photons, electrons, positrons and neutrinos, all at essentially the same temperature, all diffuse beyond any description we have. The photons are redshifted to wavelengths approaching the size of the observable universe. There are no temperature gradients, no free energy, no structures, no complexity. The universe has achieved maximum entropy. And then, nothing. Not nothing in the sense of a dramatic end. Nothing in the sense that nothing further changes. The universe isn't destroyed. It isn't consumed. It simply exists in a state of perfect thermodynamic equilibrium, forever. Cold, dark, uniform, silent. Every particle still there, just spread so thin, so even, so featureless, that nothing can ever happen again. This is where the countdown ends. Not with a bang or a collapse, with a silence so complete and so permanent that the violence of everything that came before, the Magnetars and the kilonova explosions and the gamma-ray bursters and the supermassive black holes and the merging galaxies, all of it will seem, from the perspective of the heat death, like a brief, beautiful burst of complexity in a universe that was always trending toward this quiet. You are on a planet. It is the third planet from a medium-sized yellow star in the outer arm of a spiral galaxy. The galaxy contains about 400 billion stars. The observable universe contains about 2 trillion galaxies. Everything we talked about tonight, the Magnetar, 50,000 light-years away, whose flare ionized our atmosphere. The neutron star collisions that made the gold in your jewelry. The supermassive black hole at our galactic center. The quasar that outshines 140 trillion suns. The void that might be a bruise from another universe. The something beyond the cosmic horizon that is pulling everything we can see. All of that is in the same universe as this planet. The same continuous, physical, causally connected reality. And you are in it. Right now, at this hour. There's a version of the response to tonight's content that leans toward fear. That takes the scale and the violence and the impermanence. The fact that the sun will eventually exhaust its hydrogen and expand and consume the Earth. That our galaxy will merge with Andromeda in 4.5 billion years. That in 10 circumflex, 100 years, there will be nothing recognizable as structure anywhere in the cosmos, and feels small and afraid and temporary. That response is understandable, but it's missing something. Every item in tonight's countdown is a fact that we know. Not guessed, not imagined, not believed. Measured, calculated, confirmed against observations. The kilonova event GW17-0817 was detected simultaneously by gravitational wave detectors and optical telescopes and gamma-ray satellites across the entire planet. The event horizon of Sagittarius A was imaged by a telescope the size of the Earth. The temperature of the Eridanus cold spot was measured to 7 decimal places by a satellite. We know these things. We, the species that evolved from hominids who were scraping at the African savanna 3 million years ago. We have built instruments sensitive enough to detect the merger of 2 neutron stars, 130 million light-years away, and confirm that gold was made in the collision. That is what we are. We are the universe knowing itself. We are 13.8 billion years of cosmic evolution that produced on one small rocky planet around one ordinary star, a form of matter complex enough to ask why. To build instruments to measure the answers. To sit in the dark at 3 in the morning and listen to someone describe the scale of things and feel the quiet that comes after. The universe doesn't care about us in any intentional sense. There's no evidence it was designed for us, or that our existence is its point. The Great Attractor is pulling everything in a 150 million light-year region toward it, regardless of whether anyone notices. The heat death is coming regardless of whether anyone is there to experience it. The Magnetar will flare again, and the gamma-ray bursters will go off in distant galaxies, and the supermassive black holes will keep consuming. All of it indifferent to whether any observer is present. But here's the other side of that. The universe doesn't need to care about us for the fact of our existence to matter. We are here. We are aware. We have built a civilization that has measured the distance to the edge of the observable universe, detected gravitational waves from neutron star mergers 1 billion light-years away, imaged the shadow of a black hole 55 million light-years distant, and worked out the thermodynamic fate of all matter in the cosmos. We have done all of this in about 400 years of systematic science. In a 13.8 billion-year-old universe, 400 years is less than an eye blink. What we might do with another 400 years, another 4,000, another 40,000, if we survive that long, is genuinely unknown. And that unknown is, depending on how you hold it, either the most frightening or the most exciting thing in the universe. Tonight, you don't need to hold it at all. Tonight, you can just let the scale wash over you. You've heard about the termination shock, and the Magnetar, and the neutron star collisions, and the black holes and the voids, and the Attractor, and the edge, and the beyond. You've heard the numbers. You've felt the scale. And now the scale can settle, and you can let it rest somewhere quiet in you, the knowledge that all of this is real and you are in it. On one small planet, around one ordinary star, in one ordinary galaxy, in one bubble of an expanding universe, at this hour, breathing. That is enough. The Magnetar is 50,000 light-years away. The Great Attractor is 150 million light-years away. The edge of the observable universe is 46.5 billion light-years away. The heat death is 10 circumflex, 100 years from now. None of these things require anything from you tonight. You can sleep. The universe will continue. And tomorrow, or another day, you can come back and look at it again. Good night.